So if you please.
Yeah, thank you very much, Lazar, for the introduction. Yeah, so now we know that serverless is this emerging paradigm in cloud computing that empowers both users and cloud providers. And because of its unique characteristics like short-lived functions, extreme elasticity, and so forth, there are so many intriguing problems arising from them, right? And as researchers, not only do we want to identify problems, but we really want to find solutions to them. And we don't believe things until we can build systems and measure them. But first, we need to think about what we should study, right? And we can't generate those functions and tell the world, we found problems in the generated data, and we have solutions to them, right? That's not convincing. So we really need to carefully model the workloads, especially we're very interested in the production workloads, right? And we have this very representative, highly cited workload from Microsoft Azure. And the problem here is that it spans 14 days. It's a 2-week trace. And it contains 73,000 functions. Okay. Those cloud providers are operating at such a scale that we can't just take their trace and put on our infrastructure and replay them. So now the question is, how do we scale them down so that they are representative, still representative, and we can use them in our experiments? Well, the simplest way is to do some random selections or arbitrary pick and choose. And this is actually the common pitfall in prior works. So the question is, can we do better? The answer is yes. Right? We have another weapon, which is math. So we built this trace scaler, trace sampler, if you will. We statistically shrink the trace by 1,000 times while still keeping the characteristics or distributions of those functions. Also, we provide monotonic sampling. The reason for this is that each sample is individually sampled from the original trace, right? So the number of functions in a sample trace doesn't directly translate to the load they have, right? So for example, if a trace of 100 functions can have a little bit lower load than a trace containing only 90 functions, right? And it's going to be a headache if you are going to do stress testing using this trace. That's why we provide monotonic sampling. So in this experiment, we scale down the trace to only 100 functions. And as we can see, the red line is the original distribution. It's quite smooth. And the blue line represents our scaled down trace. And they are pretty close, as you can see. And for each sample, our sampler produces, it runs 2 statistical tests. And we really validate the distributions across board. So now we have this representative trace. And what we want to do next is, as we have done in this course, is to drive the system, right? We drive the system to do the stuff so that we can measure the behavior and learn from them. And so we built this load generator to drive the system and systematically replay the trace. And also we can generate RPS using different RPS, requests per second, and to varying the load in a controlled manner, right? And also we can customize the inter-arrival time, the IAT. Also we want to collect detailed metrics so that we can learn the behavior of the serverless system. And one technicality here is that it turns out the implementation of the functions is quite crucial. So we have been talking about serverless functions, but how should we implement those benchmark functions? So we have information from the trace, how many invocations each function has in a period of time, and the execution time, also the memory. Right? The question here is that how should we implement the trace function so that they impose similar stress on the system as they did in the original production? One straightforward way to do so is, we do a sleep for consuming service time, and we just do a system call for allocating memories. And we demonstrate that this is problematic. Okay? Why? Because as the functions get shorter and shorter, those implementations is amenable to interrupts and context switches, right? And those timer-based functions, when they come back, the time has elapsed, but the work has not been done yet. And also, we touch the physical pages that allocated to us so that we can consolidate the paging. So in this experiment, we compare our implementation and the common practice, okay, the ROM implementation. And as you can see, there's a huge gulf between them, right? So on the y-axis is the medium latency, on the x-axis is the throughput. So let's have a closer look. So our implementation is bounded by the hardware. So it's bounded by the physical limitation. So what the machine can actually do, because it has solid executions. But if we look at the raw implementation, it has astronomical throughput, right? Why? Because it's not doing the actual work for the right amount of time. And we really want expected behavior in our experiments so that we know how the system behaves and how the actual throughput look like. And there is 100 times difference between the actual throughput and the throughput produced by the raw implementation. So a quick summary here is that we statistically scale down the trace so that we can analyze and study the representative workload. And we also build a load generator to systematically replay the trace. And we also demonstrate that wrong function implementation can really result in underestimation of system resource usage by 10x and 100x overestimation of throughput. So we propose and really advocate for a principled approach for serverless research.